Kicking things off on the main stage now, Jan will be giving us a talk on reimagining better health by looking at the potential of foundation models. Jan's role is to drive GE Healthcare's digital mayor's ecosystem strategy, and together with his team, develop cooperation with partner companies, indirect channels, startup centers, and networks. I'm sure you won't be able to tell it based on his appearance, but he has over 15 years of experience in healthcare informatics and also heads up GE's Edison Accelerator. Please can we give a very warm, loud applause to make sure that everyone gets out of their conversations for Jan Vega, Senior Director for Digital Ecosystem for GE Healthcare. And there's a few of us, and it's a long walk. Keep the clapping. It's a long walk, guys. It's a long walk. It's a long walk. It's a long walk.
Thank you very much.
Thank you so much.
Hey everyone, I hope you are doing well. And Maxime just said, right, for those of you who want to go to other sessions, leave the room. Please don't do this. Stay with me. And look, I hope you had a good networking session. I truly believe, right, getting in touch with each other is so important and so relevant in our industry. So maybe you want to set yourself a goal the next 2 days to connect with new people, with new faces, because all this transformational shift we want to, let's say, go through the next couple of years in healthcare, which are so important, is something nobody, no single player in this ecosystem can do on their own. So make connections and get together. Ladies and gentlemen, look, I'm sure you know, so far AI's impact on healthcare has been relatively modest, right? We have seen some interesting developments in radiology, in biopharma. We have some things we have seen in like more the admin type of systems. And in radiology, for instance, image recognition was a key breakthrough, really transforming this side of medicine. And AI has particularly been suited for radiology due to primarily 2 reasons. One is medical images, as you know, contain huge amount of data. And secondly, AI started outperforming humans in image recognition like a decade ago. GE Healthcare's digital strategy, and you heard earlier from my colleague Roland, is to look at AI to help clinicians achieve clinical and operational outcomes that create really maximum impact for patients, providers, and health systems. From our MRI scanners used by doctors to, for instance, detect tumors on the prostate gland, to mobile X-ray units in the ICU or the ER that technicians use to image the lungs of a patient at the bedside. We are seeing really tangible impact with our AI embedded on the device where and when clinicians need it. AI is an incredible lever to tackle problems at a speed and scale that our providers are coming to expect, to help save lives and improve outcomes for millions of patients everywhere. And look, advanced machine learning and deep learning has been at the core of our product development for more than a decade. We leverage deep learning for a variety of different tasks related to like object detection, segmentation, image quality improvements, reconstruction, just to name a few. I want to give you a couple of very quick examples. One of the key innovations from like last year we brought to the market is RX. RX Brain is the first of anatomy-based organ slice prescription AI features in our MRI scanners. And this AI feature allows us to deliver consistent slices from the same organs for the repeat scans of the same patient or also across patients. On the right-hand side, you can see another example. SonoCNS helps in a similar task, but during the post-3D acquisitions by automatic detection of 4 standard views in our fetal ultrasound images. And in addition to supporting auto-consistency, this AI feature also improves the sonographer workflow by reducing the number of keystrokes up to actually 80%. Another quick example is Sonic DL. This is a newly launched deep learning technology for acquiring high-definition MRI images, especially in cardiac imaging. And look, traditional cardiac MRIs had the challenges such as requiring multiple breath holds and capturing several heartbeats for complete imaging. And Sonic DL now addresses those kind of challenges by really drastically accelerating the speed of MRI image acquisition, enabling images to be taken up to 12 times faster than in traditional methods. And this technology allows cardiac MRI to be conducted within just a single heartbeat, reducing examination times and improving patient comfort. And the elimination, especially of those multiple breath holds, simplifies this overall imaging process and makes it more accessible for patients that have struggles holding their breath for a long time. It improves also the quality of cardiac imaging, reduces motion artifacts, and cuts scan time also quite significantly. Just got FDA approval for this, and we believe this has huge potential to really greatly expand patient access to cardiac MRI. GE Healthcare has been involved in supporting radiation therapy planning for the past 20 years. And the slide you can see now illustrates the radiotherapy workflow and approximate average time it takes to optimize the workflow. It's fairly clear that manually segmenting organs at risk, OARs, from radiology images is the most time-consuming step in the workflow, sometimes taking up to like 3 hours, and the automation of this step is something that would greatly benefit radiation oncologists or dosimetrists. Auto-segmentation is a deep learning post-processing application designed to automatically generate contours of organs at risk from CT images. And this tool is designed really to facilitate the initial segmentation of OARs and thereby streamlining the contouring process and assisting in radiation therapy planning. Of course, subject to user review and adjustments if this is needed. This application includes 1 deep learning localization and 15 deep learning OAR segmentation algorithms designed and trained to contour 40 different organs or organ subregions. During the application data processing workflow, a deep learning localization model, as I said, first analyzes the input CT, and then the trained deep learning organ segmentation models then delineate the organ boundaries, incrementally processing subvolumes of the CT. And then, of course, this system converts those organ contours into the right standard, a single RTSS DICOM object or series, which is automatically sent to your chosen network location, because what is important here is that this format is, of course, compatible with radiotherapy planning software. Now, let me discuss how we view foundation models at GE Healthcare, how we believe they could help us in some of our challenges, especially in scaling our approach. Earlier on, I mentioned this example of RX Brain. RX uses deep learning created from a database of tens of thousands of images to automatically detect patient anatomy and prescribe MRI slices for routine and challenging neurological and now also like knee exams, delivering consistent and quantifiable results. The automated process boosts efficiency and ensures consistent exams for ongoing patient follow-up by replicating the steps used in planning. As I said, we started with the brain as like the first anatomy for this, which took us about 2 years. And when I say 2 years, it means like almost half of this time we spent in like curating the images, and then spending the other half of the time training the model, deploying it, validating it, going through regulatory clearance. And even with some optimization, just taking what we have learned from the brain, now trying to take that to like the next set of anatomies, I mean, it took us over a year just to develop and deploy each one of those models. So this motivates us to think really more about like the direction of what we can build as a foundation model that can capture all anatomies like in a single shot, and which helps eliminate like 3 scans and also scanning inefficiency. The first one I mentioned with Eric's brain, now translated to the knee. Now we are looking into spine, into prostate, and each of these is a separate journey on its own today. And for each of these models, as I said, requires own training, which brings us really to foundation models. I think most of you agree we are likely at a turning point where, right, those rapid advancements in technology, particularly in those generative AI and large foundation models, are really reshaping all society all across sectors. And these models enable us to create new content, create new outputs, communicate, and enable us to work more efficiently. Foundation models learn from vast amount of data with minimal human input. They are very flexible to handle new tasks and different kind of data that they have not seen before. And moreover, they can generate entirely new content by pulling information from various sources. Actually, much like humans, right, using past experiences to make decisions, these kind of models can not only adapt but also innovate, impacting fields really from business to medicine to education, research, arts, software development, and so on. So, as I mentioned, currently we are working on many domain-specific AI models, which is great for our business, great for our customers, but while they meet our business needs, this approach is really not scalable for what we are trying to do at G Healthcare. I mean, we have 4 million installs, touching 1 billion patients, pretty much every modality you can imagine, imaging, ultrasound, monitoring. So, for example, we have to develop separate models for each of the RX models, and restarting the model development step from scratch every time. While there have been exciting advancements in medical AI, many of the current models are specialized for very specific tasks and need a lot of carefully prepared, high-quality data to learn from. And the drawback is that these models aren't easily adaptable to new clinical contexts. Each new deployment often demands a fresh set of data, has to be collected, anonymized, annotated, a process that is both time-consuming and costly, as you, I guess, know. Instead of proceeding this way for these and other use cases, I believe it would be advantageous to leverage all acquired healthcare data to learn the overall healthcare-specific domain. Yeah? Use generic data to learn more like the, let me call it, AI domain, and then knowledge-based synthetic data to learn any gaps in the process. By using large-scale foundation models, we can easily create specialized adaptations for various domains with, I think, significantly less labeled data, often through no-code or low-code methods. And with this approach, we are optimistic that we can achieve 10x increase in and complexity of solutions we can offer. Look, there have been recent advancements in, I would say, 3 major areas of foundation models recently, specifically as they relate to the medical field. First, as you know, right, and everybody's talking about this, large language models. I mean, for the most part, they are really specific to text, and we see very limited applications right now, especially in medical imaging. Then there is computer vision, although to a lesser context, still very exciting, especially given some of the recent advancements in the field. Look on this side, I'm sure some of you know this, right? The segment anything model, or SAM. The goal for the builders of this model was, particularly in image segmentation. And I mean, there are fairly powerful AI models that can segment any object in an image or a video with fairly high quality and efficiency. And all you have to do here is you can just draw a box around, say, a person's face, and SAM can really generate a mask of the face. It's been trained on a massive data set of, I think, 11 million images and almost 1.1 billion masks, which is, I believe, the largest segmentation data set to date. And this data set covers like a very wide range of objects, as you probably know, like animals, plants, vehicles, furniture, I mean, you name it. And the ability for these to segment any object in the image is at a bar that's really never seen before. And thanks to its generalizability and the data diversity as well, that's been trained on. And recently, we have observed improved segmentation performance for well-defined objects, especially when the prompts are less ambiguous. And this has been particularly evident in pathology. However, the performance has been less impressive in other areas, such as like brain tumor segmentation or distinguishing between gray and white matter in the brain, something which is a common challenge in medical domains. And to address this, MedSAM has been exploring fine-tuning SAM on medical datasets. The latest findings indicate that performance can be significantly enhanced through this fine-tuning process. Then there is like a new direction that's came out of Google. They use a combination of natural non-medical imaging as the foundation and then unlabeled medical images to develop strong medical image foundation models. And the pre-training strategy consists of 2 steps. One, first step involves supervised representation learning on large-scale data sets of labeled images, and then the second step involved now like an intermediate self-supervised learning, which does not require any labels at all, and instead training a model to learn medical data representation on its own. And this has demonstrated the following. To make accurate predictions in unfamiliar situations, even without needing to see the original training data. I think that's pretty interesting. This means we don't have to spend as much time labeling new data to get expert-level results. And in addition, this approach has also improved accuracy by up to, I think, 11.5% in situations this AI was already familiar with, making it even better at diagnosing issues compared to traditional methods. So overall, there is quite a significant promise in this methodology. The third exciting development is with MedPalm, or MedPalm2 specifically, another foundation model. Built on a staggering 540 billion parameters, it employs instruction tuning, medical data fine-tuning, and improved prompting strategies. And this model has set a new standard on the MedMCQA dataset, which is used for medical entrance exams in the US. And human evaluations have shown that MedPalm2, the long answers to consumer medical questions were preferred over those from physicians. The model excelled in 8 of the 9 axes relevant to like clinical utility, including factuality and medical reasoning, while also showing a lower likelihood of causing harm. And notably, it demonstrated high levels of empathy compared to clinicians. And this could be a game changer, offering physicians a powerful tool for accessing relevant information, whether through like a search engine or a chatbot in clinical settings. Let me share with you a few additional use cases or applications in healthcare. We are working on several healthcare applications, particularly in the realm of medical imaging. GE Healthcare equipment alone generates about 60% of the world's medical data, most of which is imaging and monitoring. With nearly 5.5 billion studies produced globally each year, and a shrinking number of radiologists, structuring this data for analysis can take weeks or even months. And this is where Gen AI really comes in. It can help structure this vast amount of data, easing the load on a real, already stretched workforce. And for example, Gen AI can compile a patient's entire 10-year history, summarizing the progression of a tumor by correlating past and current radiology reports, lab results, and even genetic information. It can then generate summaries for both the patient, like in layman terms, and the referring specialist. And what's, I would say, revolutionary is that generative AI can do all this in an interactive, self-supervised manner, allowing radiologists to intervene only when necessary. And instead of maintaining hundreds of separate models for each task, we have one large model that serves multiple purposes. It can handle both structured and unstructured data, interact bidirectionally with images and text, and integrate seamlessly into existing workflows for radiologists and clinicians. So, from my perspective, generative AI is not just a tool, it's a multi-purpose solution that can redefine how we handle healthcare data. Another application, and maybe you have seen this a couple of months ago, for large language models in this example, is to track care pathways and recommend next steps based on medical guidelines. These guidelines are intricate documents that outline various treatment options, depending on a patient's specific characteristics and medical history. And when followed consistently, they can significantly enhance patient care. And large models can make a real difference in this context. They can analyze these complex guidelines and provide personalized recommendations, ensuring that care pathways are followed accurately and effectively. And this not only improves patient outcomes, but also streamlines the healthcare process. Just quickly, another really interesting example, this came up really as soon as ChatGPT was launched in November 2022. On the left-hand side, you see Clifford Sturmer. He's a rheumatologist in Florida, and he uses this AI chatbot now to draft letters to insurance companies explaining why certain tests are necessary for his patients. Yeah? The technology has saved time and effort for him, although it's not without limitations, of course. Yeah? He discovered that some of the references generated by ChatGPT were not accurate, so the letters still require human review. And despite this, the technology has sparked conversations among healthcare professionals about its potential applications, of course. On the right-hand side, Microsoft and Epic have recently integrated GPT into EHR systems to auto-generate responses to patient messages. And this integration extends to Epic's hospital database, enabling people without technical expertise to ask general questions to the AI, eliminating the need for data scientists to perform specific queries. And here another example also, this came up pretty quickly after ChatGPT was out, from a young student at Stanford, Varun Shenoy. He has linked ChatGPT to his iPhone's health data, allowing him to interact with his own digital health history. Yeah? When he shared this with the public, I mean, at that point, he could only access 2 weeks worth of specific health metrics like step count and sleep patterns. However, the potential really exists for a future where everyone has a personalized AI health assistant. And this could really track your health data securely, understand your individual needs, and offer customized advice. You could ask it questions about symptoms, training plans, or even your latest cholesterol levels. Look, the potential for foundation models in healthcare is vast and transformative. Innovators around the world, like you guys, are exploring potential healthcare use cases for this type of technology. I just want to point out one thing. In the pursuit of ethical AI in healthcare, it is imperative to prioritize things like data privacy, minimize bias through proper feedback loops, and ensure rigorous validation of models, all while responsibly grounding generated information with credible sources. Upholding these principles not only leads to safe and accurate healthcare outcomes, but also fosters equitable access for all while enabling systems to differentiate between reliable and unreliable responses. Thank you very much.
Thank you very much, Jan. So that was a wonderful presentation. We've got time for one quick question. So can I squeeze over into the audience? Oh, someone's got a hand up. Where? Oh, over there. Thank you. Thank you for the wave. It helps. So as always, yes, stand up. Name, where you're from.
Hi, I'm Gurmat Sandhu.
Oh, hold on. Try again.
Can you hear me now? Perfect. My name is Gurmat Sandhu. I'm from Basel. I'm an AI practitioner in healthcare. So Jan, you presented a very compelling argument, for example, the image analysis in terms of diagnosis. So any thoughts on how you would frame the value assessment of such technological advances? And then if you've got time, how would you frame the ROI on this?
Yeah, thank you very much. I mean, this is two great questions. Look, first of all, maybe to add to this, when it comes to generative AI, for me it seems like there are like of two different worldviews right now. Right, one is more the large language model perspective, right? Healthcare data documents, right? Get it through this model and get, let's say, the outcomes you want. And there is this worldview of multimodality, right? How can we use generative AI to open the door to multimodality, something very important because we all know all those point solutions, discriminative AI we're using today, this is not how medicine works, right? Medicine has always been very multimodal, and we need to get to this with AI as well, and generative AI will be the door opener. There's a lot, right? The two questions you mentioned, there's a lot of things we as an industry, we as an ecosystem have to think through and find the right approaches and processes. So I don't have a specific answer to this, to be very honest, at this point in time.
Brilliant. Thank you so much for that question. And thank you so much again, Jan. Can we now have a huge round of applause for Jan?
Thank you.
Thank you so much.